Okay, so today our speaker is Riya Dogra, and the title of her talk is A Survey of Compact Matrix Quantum Groups and Banica-Speicher Quantum Groups. Please.
Yeah, 1 second. Is my screen visible?
Yes.
Okay, all right. So I'll start now. As we are well aware that the study of symmetries in math, it's quite an important tool to learn how the geometry of a certain considered object looks like. In this case, what we want to do is we want to understand the symmetries in an operator algebraic context. So basically, we want to see what a symmetry should be in the non-commutative context. Starting off, we just recall the conventional examples for groups as symmetries. If we have a finite set with n elements and we take its group of automorphisms, then it is exactly the symmetric set on n elements, and it acts on the finite set by permutations. In the same spirit, another example we have is of the sphere and the group of its isometries, and that group is isomorphic to the orthogonal group. Now we start off with some well-established results. If we start with a compact Hausdorff space X, then we know that the space of all continuous linear functions on X, it's a unital commutative C-star algebra. And conversely, if we have a commutative unital C-star algebra A, then it is isomorphic to a space Cx, where X is exactly defined as the spectrum of that algebra A, and it's given by all non-zero star homomorphism. This comes from the Gelfand construction, and that is a compact Hausdorff space with the weak star topology. So what this basically tells us is that we can identify compact topological spaces with commutative unital C-star algebras. So therefore, in a sense, non-commutative C-star algebras may be viewed as non-commutative function algebras over the so-called quantum spaces. And therefore, the theory of C-star algebras, it turns into a non-commutative topology. So now starting off with definitions, the first one we have is of a C-star algebra. Conventionally, it's a Banach algebra with an involution such that it satisfies the C-star identity, which is this one. And there's a very well-known characterization of a C-star algebra also, which is just that it is a norm-closed star subalgebra of the space of the bounded linear operators on some Hilbert space H. Now we want to know what a universal C-star algebra looks like. First of all, it's described by a set of generators and relations. And these can be, in some context, be realized as bounded operators on a Hilbert space because of this characterization of a C-star algebra. And so starting off these, first of all, what we do is we take a set of generators E, and then we consider the set of all non-commutative polynomials and in E, and we denote it as PE. And then we take a subset of this set of polynomials and denote it R. And then we generate an ideal from with respect to R. And now we're ready to generate the universal star algebra. It is nothing but the quotient of this space PE with the subset R. No, wait, with the ideal generated by R. Yeah, it's given here. And now we need a norm on the star algebra. We also denote the star algebra as A. And this norm is nothing but the supremum norm over all values of Px, where P is a C star seminorm. And note that if the value of this norm is finite for every element in A, then the star algebra is defined to be the universal C star algebra generated by this set E and the set of relations R. And it is formally given as the completion of this quotient in the norm that is defined here. Now that we know what a uh, universal C star algebra looks like, we see what the universal property states. So if we have an arbitrary C star algebra B such that the subset of B, which is given by these elements, these satisfy the relations for the set E. Then there exists a star homomorphism, which from the universal star algebra, which we constructed before, to the algebra B that we are considering. And this star homomorphism basically takes all generators in the universal algebra to all the generators here, yi in B. For a concrete example, we see the C star algebra, which is generated by U and 1. And these generators are such that they're all normal. U's are normal and their value is equal to the multiplication with the involution is equal to 1. And this universal star algebra is isomorphic to the C star algebra associated to the sphere. And another, for these couple of examples, these are when a universal star algebra might not exist. So for example, if the universal star algebra is given by this relation, then it does not exist because its norm might not be finite. And for example, if the generators look something like this, then because the generators are realized as some bounded operators on some Hilbert space, and we see that for any two bounded operators, this relation cannot be satisfied. So therefore, this star algebra will also not exist. Now now that we know what a C star algebra looks like and what a universal C star algebra is, we are ready to state the definition of a compact quantum group. A compact quantum group, first of all, it's a unital C star algebra A, and it is also equipped with a co-multiplication delta. A co-multiplication is a unital star homomorphism, which is a map that looks like this, such that these following relations are satisfied. The first relation is nothing but the co-associativity of the map co-multiplication. And these two spaces, which are defined as here a span of these elements, they are respectively dense in the minimal tensor product of A with itself. And once we have a star algebra that satisfies these conditions, we can denote it as a tuple. So which A is a base algebra, and okay, this is a typo, this is delta, and delta is a co-multiplication, a unital star homomorphism that makes it into a compact quantum group. All right. So compact quantum groups can be seen as a generalization of compact groups. To see that this makes sense, we start off with a compact group G. Then we deduce that the algebra CG is a unital C star algebra and delta is co-associative. This happens because G is a compact group, we use the associativity of G in order to show that delta is co-associative, and that is explicitly given here. We can verify this for any two elements F1, F2 in CG, and then extend it by linearity over the whole algebra. And therefore, we can deduce that every compact group is a compact quantum group. For the converse, if we start off with a compact quantum group, which is given by us, first of all, a C star algebra A and a co-multiplication delta, and suppose that A is commutative, then it is isomorphic to CG, where G is nothing but the spectrum of A, as we discussed in the first couple of slides. Also, the co-multiplication is given like this, which induces a map on G cross G to G, which takes the spectrum of the tensor to the spectrum of the algebra itself explicitly by this map. And similarly, as the previous case, the co-associativity of delta will give us the associativity of the multiplication M. So therefore, this implies that G is a compact semi-group. And now to deduce that it is actually a compact group, we use a couple of basic results in group theory, which say that if these two linear spaces are dense in this tensor product, then it has the cancellation property. And we know that this density holds true because of the definition of a compact quantum group, and that is what A is. And now that the cancellation holds, then it is obvious that a semi-group with the cancellation property is a group. So now looking at this was an example of a commutative compact quantum group. And now we look at an explicit example of a non-commutative case. And we start off with group algebras. First of all, if we have a discrete group G, we can associate a C star algebra to it as given. So this is nothing but finite linear combinations of the elements of the discrete group G, and the coefficients come from the complex field, the field of complex numbers. And then this set, it forms a star algebra, and the multiplication is given as this, where the coefficients get multiplied with each other. And the involution is given by the linear combination, where the coefficients are taken to their complex conjugates and the group elements are taken to their inverses. Now, once we have this set, what we do is we take its completion with respect to this norm. The norm of X is given by the supremum over all representations of the group algebra of G in some Hilbert space H. And once we have this norm, then we consider the completion of the set CG with respect to this norm, and then we denote it as C star max. What happens is that this space C star max, it is isomorphic to the universal C star algebra, which is given by these generators, where UG are, where G belongs to the discrete group G that we started with. And the multiplication of these two generators are given as this herein. And the involution is given by, I think this needs to be in the subscript. Yeah, so the involution is given by its action with respect to the inverse of the element. For example, if the discrete group we're starting with is the group of integers, then the star algebra associated to it is exactly the one associated to the sphere. And again, if the group we're starting off with is non-abelian, then the max star algebra is non-commutative. So this is one of the very conventional ways to construct non-commutative C-star algebras. Similarly, we can do the same with the reduced group C-star algebras, and that will also give us compact quantum groups. First of all, we consider the left regular representation of G and lambda, and it acts on CG and takes it to some the space of bounded linear operators of the little L2 space. And it is defined in terms of the orthonormal basis of the little L2 space of G. Now, the faithfulness of this representation lambda, it implies that the image of the group algebra of G under this representation is isomorphic to the group star algebra. And then we define the reduced star algebra of G as the completion of the image of this representation inside the space of bounded linear operators of little L2G. And we consider the same norm as we did in the last example. And then we also exploit the existence of the natural map from the max star algebra to the reduced one. So basically what we do is the co-multiplication is also just induced by the one that was given in the last example with respect to the left regular representation lambda that we are considering. Explicitly, the map is given by this composition, and this implies that the reduced star algebra is also a compact quantum group. Right, now moving on from examples. Now that we know what a compact quantum group is defined as and looks like, we want to see how it acts on any arbitrary C star algebra B. So an action, first of all, it's a unital star homomorphism, and let's denote it as alpha, such that these two criteria hold. And one very concrete example of that demonstrates how an action works is the quantum permutation group. Excuse me. All right. So this example is for the quantum permutation group. Again, we start off with a finite set of points and consider its group of automorphisms. And then we associate to it the C star algebra is this, it's not universal yet. So it is nothing but it's generated by n projections such that they all sum up to 1. And because such projections, they form a basis. So any action of an arbitrary compact quantum group A on this algebra is explicitly of this form, where a projection Pi is taken to the linear combination of its tensors with the elements of A. And these elements, they satisfy some nice relations, and I skipped that part. So basically, I'm trying to get at the definition that was given by Wang of a universal star algebra. This is also a very conventional universal star algebra. So it is generated by elements uij, where ij they go from 1 to n with respect to how many elements were in the set we started off with. And all of these elements, they're projections, and they sum up to 1. So they can be seen as all the rows, and all the columns, they sum up to 1. And along with this algebra structure, it also has a co-multiplication structure, which is defined as so any element uij, the co-multiplication map takes it to u dash ij, which is just given as a sort of an analogous for matrix multiplication. So because the uik and uil, these are orthogonal for non-identical indices. This follows from the fact that they're projections and sum up to 1. So this implies that the co-multiplication also takes them to projections, which is proven here. And it also satisfies some other nice identities. And then we use the universal property of the definition of this algebra. And so therefore the map delta that is defined here, it is actually a star homomorphism from the universal star algebra to the tensor to its tensor with itself. All right. Now we move on to some properties of compact quantum groups. A little definition. If A is called a quantum subgroup of B if we have a surjective map phi such that this condition is satisfied. And now, in the spirit of the definition of the star algebra we defined in terms of projections, we are ready to state the definition of compact matrix quantum groups. So starting off with a natural number n, a compact matrix quantum group, it is defined as a pair, AU, where first of all, A is a unital C-star algebra. And again, it is generated by elements that look like this, and ij, they range from 1 to n. And they form the entries of the matrix. All the elements are invertible, and so is their star operation. And the map, the co-multiplication map that we defined before, is actually a star homomorphism. And this is just the notation. We describe it with the same notation as we did the old compact quantum groups. An example is the unitary quantum group, which is denoted by UN. It is the free unitary compact quantum group. It's given by the generators, which look like this. Again, uij. Ij range from 1 to n, except u and its involution, they're both unitary. And if these elements uij are taken to be commutative, then the condition unitary is implied, but otherwise it's not, and it might not give rise to a compact quantum group at all, because it might not be invertible. All right, now we discuss the representation theory of compact quantum groups. First of all, for any given group A, there exists a unique Haar state such that this condition is satisfied. And similarly, we can there exists a unique Haar state on the reduced version of a compact quantum group also. And again, it is given by exploiting the natural maps that we defined before. And first of all, the reduced version is denoted as A red and delta red, where the algebra is the image of the algebra in the linear space of bounded operators on H, which was defined before, but we had defined it for the case of L2G. And the Haar state of the reduced version is analogously defined as this. Also, the Haar state on an arbitrary compact quantum group, it might not be faithful, but for a reduced version, it's always faithful. Now we define the tensor product of two compact quantum groups. If A and B are two groups, then their tensor product is given by the max tensor product of the underlying algebras, and the co-multiplication map is given by this composition, where rho is defined as follows. Its Haar state is also given as a tensor product of their individual Haar states, and the tensor is a compact matrix quantum group if A and B are both compact matrix quantum groups. So now we define the concept of a representation. If we start off with a unital C-star algebra with a co-multiplication delta, then a finite dimensional representation is, first of all, it has a matrix form, and it is given as this expression. So the co-multiplication, it takes the matrix elements to the linear combination of their tensors. Again, it's just the definition of how the co-multiplication was given for a compact matrix quantum group. Now, if U and V are two representations, then we can define the tensor product of the representations, and it's given as this expression where the terms E alpha beta and E gamma delta, they belong to the matrix groups respectively, and the UV elements, they belong to the algebra A. And we also define another element, U bar, which is given as the linear combination of the matrix elements along with the involution of the algebra elements. So now if we have two representations, then, and consider a linear operator T, which is a bounded linear operator from HU to HV with respect to the representations U and V. If this identity holds, Tu is equals to Vt for any two arbitrary representations U and V, then we say that T intertwines these representations. And these two representations are called equivalent if there exists such a linear operator T, such that it's also invertible. And now irreducibility is also as one would expect of a representation. It's irreducible if every intertwiner T is of the form scalar multiple of the identity map. Similarly, if U is an irreducible representation, then its bar that is defined here, it is also irreducible. And if it's irreducible and unitary, then U bar is equivalent to a unitary representation, which means that there exists an invertible intertwiner between U and U bar. And now representations can be decomposed as is expected. So every non-degenerate finite dimensional representation is equivalent to a unitary representation. And these are also some very straightforward basic results that hold for representations of compact quantum groups as well. So now we move on to the definition of a W star category. We start with a set of objects R, and we equip it with a binary operation dot, or just any symbol. And then we consider a family of finite dimensional Hilbert spaces. And for any two objects inside that set, we define more of RS to be a linear subspace of the bounded linear maps between HR and HS. So then this quadruple, which is just that the set of objects, the binary operation, the set of the family of finite dimensional Hilbert spaces, and the linear subspace of the bounded operators, then it's called a concrete monoidal W star category if some conditions hold. So the first condition is that for every object R, the identity operator acting on HR, it has to belong to the Moore subspace defined. And if A and B are part of the subspaces as mentioned, then BA is also, if BA is a part of the Moore space of R double dash. And for any two arbitrary objects in R, if A is belongs to the subspace of the bounded linear operators that is being considered, then its involution is in the subspace of the bounded linear operators from, well, the opposite side, from HS to HR. And if those two spaces are equal, then the identity of R, an identity of R is also in the subspace, that the linear subspace of the operators, then R is equal to S. Again, if we have two linear operators A and B in these subspaces, then their tensor product is given as an operator in the linear subspace of bounded linear operators which go from HRS to HR dash S dash for any four objects in R. And this is associativity and the existence of a unity. And up till here, if these seven conditions are satisfied, then this quadruple is called a monoidal W star category. And that category is called complete if, in addition to the seven conditions, it also satisfies these three conditions. So for any object R and any unitary map from in between HR and any arbitrary Hilbert space K, there exists another object R such that the arbitrary Hilbert space coincides with the space with respect to that representation S. And V lies, and V is also a linear operator, bounded linear operator between HR and K, which is HS, and also lies in the subspace that is being considered. Similarly, it should also satisfy these two conditions for an arbitrary object R and an orthogonal projection that lies in the Morse subspace. And for any object R and any orthogonal projection in the Morse subspace, there exists another object S such that the Hilbert space with respect to S is given as the product of the projection into Hilbert space with respect to R. And if this follows, then the category is said to be complete. The third condition just gives the canonical embeddings. All right. So that was quite a lot of conditions to remember, but now we move on to the representations of a CQG. They actually form a W star category. And why we're doing this is because these representations they form a W star category, but even if we start from a category, we can get back a compact quantum group, which is why it's sort of interesting to see how they interact. So if we start off with a compact matrix quantum group, then we define some terminology. By rep G, we denote the set of all finite dimensional unitary representations of G. And the Morse subspace is exactly those linear maps which satisfy these conditions. dV is equals to WD with respect to the two elements V and W. And so this is this is the space of intertwiners. So T is an intertwiner as we defined earlier if this condition holds. And with these objects, so the set of all finite dimensional unitary representations, the binary operation is the tensor product and a family of finite dimensional Hilbert spaces and the subspace defined here. They form a complete concrete monoidal W star category. So basically all the 10 conditions we discussed before is satisfied by the representations of a compact quantum group. And in relation to the representation theory, Tanaka Krein, they gave a very nice theorem. So it says that let the quadruple be denoted by R and let it be a concrete monoidal W star category such that F and F bar it generates R. Yeah, for F and F bar reference, skip the last line. So they belong in rep G. So then there exists a compact matrix quantum group such that the completion of rep G, the set rep GR, is given as the completion of the category. So also the group that is generated by A and U in this context, it's also universal in the following sense. So if there exists another group, say G dash, it's also a compact matrix quantum group, such that the object set of objects that we're considering, it lies as a subset of the rep G dash. Then there exists a homomorphism from A to B and from where U is mapped to B. So yeah, this is what I was talking about. If we start off with any compact matrix quantum group, then its representation theory forms a W star category. But the converse is also true. If we start off with any category, we can get a compact matrix quantum group. So therefore, there's a way of producing groups by specifying the representation theory. For example, before in the examples we saw, we specified by using group algebras and then reduced group algebras, and this is another way of getting concrete compact matrix quantum groups. All right. So now we want to introduce what Banach-Speicher quantum groups look like. For that, we look at the category of partitions. First of all, a partition is defined as a decomposition of k plus l points. We look at partitions that look like this. Basically, we take two elements, k and l. K are called the upper elements and l are the lower elements. And as one would expect, a partition is just their decomposition into disjoint subsets, and they're called blocks. So basically what happens is that if k are the upper elements, then they are denoted by the blocks on the upper side, and the elements in L are denoted as the blocks on the lower side, and they're just connected by lines. So this is how a partition can be represented in a block form. So for example, here k is 2 and L is 4, and this is 1, 2, 3, and 4. This partition has 4 disjoint subsets. And similarly, this is a partition for P41. Now, if we have two partitions, P and Q, with respect to some number, some integers k, l, k dash, l dash, then their tensor product is given as, first of all, it's obviously the partition, the elements get added up, and the partition is obtained by placing their blocks side by side. So if this is a partition of 2, 4, and this is a partition of 4, 1, then if you just sort of take away the tensor product sign and place them together, it forms a partition of 2 plus 4, 6, and 4 plus 1, 5. Now, any two partitions can be composed by concatenating, but not side by side, but putting Q under P. So basically something like this. So the composition is a partition. It's obtained by, we align the lower points of the first partition, say P, and along the upper points of the partition Q, and the middle points are ignored. For example, this is a middle point, and this can be ignored, and they're just removed. And now there's another operation, involution. If P is a partition, then its involution is just the partition that we get by turning it upside down. So for example, if this is a partition, then its involution is given by turning it upside down. All right. So now when we have this sort of space of partitions, which, and with some operations defined such as tensor product and involution, there are some other linear maps and operations defined on it. What we're trying to do is we're trying to make the space of partitions into a W star monoidal category so that we can get some compact quantum groups through that category. So discussing some linear maps, if P is a partition and N is any fixed natural number, then the map TP is a linear map, and it is just defined as given. And the set the i's and j's, they're all indices, and EIs are the canonical or orthonormal basis of the space complex numbers, the nth power of complex numbers. This is a typo. This is the field of complex numbers. And again, their bar is also defined as follows. So if we label the upper points in the partition P with the indices i's, and the lower points with j's, then then the bar is 1, value of delta on the bars is 1 if the partition connects only the equal valued indices, where the indices are given by i's and j's, and otherwise it's 0. So that is the delta function on i's and in the bars of partitions. And now, as is expected, the operations on partitions, they also passed onto linear maps. So if we have two partitions P and Q, then their tensor is just the map which is mapped with respect to the tensor of partitions. And the composition of two maps with respect to partitions is given by this normalization multiplied by the map with respect to the product of these partitions. And alpha here is the number of removed blocks in the composition, as we saw earlier. And again, the involution of a map is given by the map with respect to the involution of the partition. And now we're ready to define the Banach-Speicher quantum groups. So given a compact matrix quantum group, it's called Banica. Oh, right, sorry, this is a typo. It's Banica-Speicher. And it's called Banica-Speicher quantum groups if the symmetric group is a subset of G and G is a subset of the orthogonal group. And if there's a category of partitions such that the Moore subspace, which is considered in the quadruple of the category, is nothing but the span of all the linear maps associated to the partitions. So now we try to move from categories of partitions to W star categories. So again, we start off with a category of partition C and a natural number n. Now we're forming the objects that we need in the quadruple. The set of objects R is nothing but the set of natural numbers inclusive of 0 with the binary operation as addition. And okay, I think this is a typo. I think it might be the field of complex numbers. Yeah, these are the family of Hilbert spaces. And the subspace, the Moore subspace with respect to R and S, they are given by the span of all these maps with respect to P, where P are all partitions in the category we are considering. And this basically defines a W star category and it's generated by 1. We name this category as R. And then there's another theorem that relates the representation theory of compact matrix quantum groups to Banach-Speicher quantum groups. So if we have a category of partition C and a natural number n, we can obtain a compact matrix quantum group by the previous theorem and by the representation theory of compact matrix quantum groups that we discussed earlier, because they form a W star category. And it is a Banica-Speicher quantum group where this holds, because that's how it was defined. And precisely it can be written as this. I'm sorry, I did not get to actually read this theorem in detail. So there's some missing details here. I'm not exactly sure what a model of the W star category is. So if someone knows, they might be able to help me. Okay, so overlooking this theorem for now, what we basically have is that there is a one-to-one correspondence between the combinatorics of categories of partitions and Banica-Speicher compact groups. And that is it. If there are any questions.
Okay, thank you, Riya. Could you show me once again, please, the last theorem about the, this one. Yeah. So my conjecture, I of course, I'm not sure, but my conjecture is that, is that correct that the representation category of A is equivalent to, maybe not to C itself, but to, probably has to see it. And if yes, then it's not clear for me how it depends on the choice of little n, of the natural number n.
Yeah, actually, I'm not exactly sure what happens when something is a model of a W star category, because I remember reading it, but I sort of missed out on putting it in the presentation. So it was a quadruple along with some extra relations. and that probably satisfies these things, but I'm not exactly sure right now what a model means.
So we start with a category of partitions and the natural number. Then we generate the W star category out of this data. And then we, by using the Tanaka crane duality, we generate a compact quantum group. And the point is that the category of representations of this quantum group is equivalent to this W category. And everything, of course, depends on the choice of n, probably. Is that correct?
Yeah.
Yeah, I see. Okay, thank you.
Thank you.
More questions, please. Oh, I have one more question about the representation spaces. Could you show, please? Yes, the construction of the closer to the end. I mean the construction of the W star category out of the category of partitions. Maybe the next slide. Not here.
Yeah.
Oh, here. So HR. So HR is probably it should be Cn to.
Yeah, I think it's the field of complex numbers, maybe.
Yes, H0 is the complex numbers, but HR is probably some tensor power of Cn.
Yeah, yeah.
Because the operators, our operators TP act. So the construction of these operators is that the operators act on between tensor powers of the same space Cn, C to the power n. So probably HR is also the respective tensor power of Cn.
Yeah, that makes sense.
Okay, thank you. More questions, please. Okay, if there are no more questions, then we thank the speaker for the very nice talk. Thank you, Riya.
Thank you so much.